Consider the opening moments of a nuclear exchange. It begins with a submarine beneath the Pacific submerged for 2 months. No GPS, no stars, no radio fix of any kind. And yet, through the continuous accounting of its own motion, it has kept track of its position on Earth with enough precision to deliver a weapon to a target thousands of miles away. On command, it launches a ballistic missile. For the next half hour, that missile will arc 4,000 miles across the planet, guided by nothing but its own inertial sense of motion and a handful of mid-flight star sightings. No ground control, no radio uplink, no one at the controls. And when the warhead falls back through the atmosphere on the opposite side of the planet, it will strike within the length of a soccer field of a coordinate chosen years in advance. Every element in this chain, the submarine, the missile, the warhead, finds its way almost entirely self-contained, and yet the same principle is now so commonplace that a version of it can be found within every phone. This is the story of inertial navigation. In 1743, an English sea captain named John Serson unveiled a curious instrument he called the whirling speculum. It consisted of a mirrored spinning top that held itself level no matter how the deck beneath it pitched or rolled. By catching the sun's reflection on its surface, a navigator could find the true horizon through heavy seas, and it became the earliest known precursor to the gyroscope, and the first time the stability of a spinning body was ever put to work as a tool of navigation. In 1817, German astronomer Johann Gottlieb Friedrich von Bohnenberger invented the first device that resembled a modern gyroscope. Bohnenberger's apparatus, referred to as the machine of Bohnenberger, consisted of a heavy, symmetrically built ball which could rotate freely around its center of gravity, suspended within 3 concentric rings called a gimbal, with each able to rotate on a different axis. This design allowed for the demonstration and study of the principles of rotational motion. Walter R. Johnson was among several individuals who independently invented the gyroscope in the 1830s. Johnson called his invention the rotoscope, and unlike Bohnenberger's machine, the spinning element was a disc. Ultimately, French physicist Léon Foucault would be credited with inventing the gyroscope in 1852, both coining and popularizing the name itself. His version of the gyroscope was designed to demonstrate the Earth's rotation in a groundbreaking manner, allowing for 10 minutes of motion experimentation at a time. A gyroscope operates on the principle of the conservation of angular momentum, which states that the angular momentum of a rotating object will remain constant unless it is influenced by an external torque. When a gyroscope wheel spins, it maintains its orientation due to the angular momentum generated by the spinning motion. The magnitude of this angular momentum depends on 2 things: how fast the object is spinning, or its angular velocity, and how much mass is distributed away from the axis of rotation, or its moment of inertia. The faster the gyroscope spins, the greater its angular momentum, and the more it resists changes to its orientation. Gyroscopic precession is a phenomenon that occurs when force is applied to a spinning object. Instead of moving in the direction of the applied force, the gyroscope moves perpendicular to it. This is because the applied force creates a torque, and due to the gyroscope's rotation, the effect of this torque is manifested in a direction perpendicular to the force. The torque tries to change the direction of the gyroscope's angular momentum, but due to the conservation of angular momentum, the gyroscope instead precesses around the axis of the applied torque. While early inertial navigation systems were robust against jamming because they required no external references once initialized, our modern digital navigation is exactly the opposite. We are constantly connected and exposed to the open web, which is why this video is sponsored by NordVPN. NordVPN provides a comprehensive suite to secure your internet traffic. For instance, when you connect to public Wi-Fi at a local cafe, you risk falling into a trap like an evil twin man-in-the-middle attack. Criminals can quickly insert themselves into the network to harvest harvest the sensitive data you enter. NordVPN encrypts your online traffic at all times to keep nefarious elements out. Beyond basic encryption, NordVPN features Threat Protection Pro. Unlike regular VPNs, this certified tool actively protects you against fake web stores designed to mimic legitimate outlets to steal your money. It also automatically scans the websites you visit to block phishing sites before they can cause harm, and it even checks your downloading files for malware, removing them if they are found to be infected. On top of NordVPN's layer of security, when I travel, I can count on it for access to the streaming services I already pay for back home without the buffering you get on slower VPNs. Nord is genuinely the fastest one I've used. Become safer online with a single click. Head to NordVPN/NewMindVPN to get an exclusive NordVPN deal plus 4 months extra. It's risk-free with Nord's 30-day money-back guarantee. At the dawn of the 20th century, German art historian and inventor Hermann Anschütz-Kaempfe became intrigued with the challenges of polar navigation, where traditional magnetic compasses are less effective. This led him to develop the gyrocompass, a tool that could maintain a consistent reference direction regardless of external magnetic influences. A gyrocompass contains a rapidly spinning rotor mounted within gimbals, allowing it to rotate freely. This rotor maintains its orientation due to gyroscopic inertia. However, unlike a standard gyroscope, a gyrocompass is designed to align with the Earth's axis. This alignment is achieved through the interaction of the Earth's rotation and gravity with the spinning rotor, creating a torque that causes the rotor to precess, gradually shifting its orientation. The gimbals play a crucial role by allowing the rotor the necessary freedom to align itself with the Earth's axis. This process, although not instantaneous, results in the gyrocompass pointing towards true north or geographical north, independent of magnetic influences. The gyrocompass's ability to resist interference from magnetic anomalies or nearby metallic objects makes it highly reliable for navigation, especially in regions where magnetic compasses are less effective. In 1905, Anschütz-Kaempfe, along with Frederick Treitsch, founded the first firm Anschütz-Kaempfe, dedicated to manufacturing gyroscopic navigation instruments. The first commercial ship with an Anschütz gyrocompass was the passenger ship Imperator of Hapag Line in 1913, marking the beginning of the commercialization of gyroscopic instruments for practical use in navigation. In 1910, American inventor Elmer Ambrose Sperry would form the Sperry Gyroscope Company to manufacture gyroscopic navigation equipment. As the company grew throughout World War I as the Sperry Corporation, the newly emerging field of combat aviation created a demand for a broad range of gyro instruments. One of their most popular instruments was the gyro horizon or attitude indicator. Much like the machine of Bohnenberger, this instrument uses a gyroscopic effect to display deviation from a set horizon. However, it does this in two axes, showing both the pitch and roll of an aircraft via a gimbaled gyroscope that is kept spinning using the suction of an engine-powered vacuum pump. Beyond simple instrumentation, Sperry also pioneered the use of gyro stabilization. In a gyro-stabilized system, a gyroscope's resistance to changes in its orientation is used as a feedback mechanism to counteract the overall motion experienced by the system. This is typically achieved by using motors or other mechanisms to apply torque based on the gyroscope's feedback. Gyro stabilization would prove to be a valuable tool for creating both stabilized gun sights and bomb sights. Beyond this, when an attitude indicator is paired with a manually aligned variant of a gyrocompass known as a directional gyro or heading indicator, the entire aircraft can be put into gyro stabilization using feedback to drive the flight controls, effectively creating an autopilot, one of Sperry's early groundbreaking innovations. World War II was a pivotal time period for the advancement of gyroscopic technology, as it marked the transition from simple instrumentation to far more sophisticated navigational mechanisms known as inertial navigation systems or INS. Inertial navigation systems use gyroscopes and other motion sensors, such as accelerometers, with a computer to continuously calculate the position, orientation, and the velocity of a moving object without the need for external references. Originally developed for rockets, simple gyroscopic systems could be found on early experimental rockets, with the concept quickly becoming an integral part of rocketry. Germany's V2 rocket guidance systems contained one of the first deployments of inertial guidance technology with its guidance, navigation, and control system that was driven by two electrically powered gyroscopes and a lateral accelerometer. The V2 system employed a simple analog computer to adjust the azimuth for the rocket in flight, driving 4 graphite rudders within the rocket's exhaust stream for flight control. An inertial navigation system typically consists of a computer and a sensor system called an inertial measurement unit that consists of accelerometers, gyroscopes, and other motion sensing devices. Initially, the INS receives its position, velocity, and orientation from an external source such as a human operator. Subsequently, it independently calculates and updates its position and velocity by processing data from these motion sensors. One key advantage of an INS is its self-sufficiency, requiring no external references once it's initialized. This independence from external references makes it robust against jamming and deceptive signals. The INS can effectively detect changes in various aspects of motion, geographic position, velocity, and orientation. It accomplishes this by measuring linear acceleration and angular velocity applied to the system. Gyroscopes specifically measure the angular displacement, and by utilizing the initial orientation as a starting point and integrating angular displacement, the system can continually determine its current orientation. Accelerometers, on the other hand, measure linear acceleration relative to the moving vehicle's sensor or body frame. They sense changes like forward acceleration, deceleration, upward and downward forces within the vehicle. However, they are unaware of their absolute orientation relative to the Earth since they move with the system. To determine linear acceleration in the inertial reference frame, the system integrates the current angular velocity and linear acceleration measured relative to the moving system. This integration, using the initial velocity as a starting point, yields the inertial velocities. Further integration, employing the initial position as a starting point, yields the inertial position. The computers used in early INS systems were either mechanical or electrical analog devices that lacked the ability to process signals. Because of these limitations, calibrated levels of damping were used on some gyroscopes to perform mechanical rate processing. By limiting the free motion of a gyroscope through a spring in one axis, a rate gyroscope is created. This concept can be taken even further with more sophisticated forms of damping. Known as rate integrating gyroscopes, the gimbal precession could be regulated by a heavy viscous damping fluid or similar damping mechanism to determine rates of angular change integrated over time. While gyroscopic INS technology revolutionized guidance and navigation post-World War, one of the fundamental challenges they face is the issue of drift. Drift in an INS refers to the gradual accumulation of errors over time, leading to deviation from the true path or position. The root cause of drift in an INS lies in its reliance on accelerometers and gyroscopes to continuously calculate position, velocity, and orientation by integrating incoming data over time. While these instruments can be made to be highly accurate, they are not perfect. Small errors such as bias in the gyroscopes or noise in the accelerometers can accumulate. Since the INS calculates its current position based on previous data, any error, however small, gets integrated into the subsequent calculations. This integration of errors leads to drift, which grow over time, making the data increasingly unreliable. Compounding the issue is the fact that INSs operate in a closed loop, meaning they do not reference external sources for correction once initialized. This isolation from external reference points is both a strength and a weakness. It allows INSs to function in environments where external correction is unavailable or unreliable, but it also means that there is no external data to correct any integral errors that may accumulate. The first INSs, for example, would drift as badly as 1 nautical mile per hour of operation. Shortly after World War II, the United States would field its own ballistic missile, the SM-65 Atlas ICBM, based on Germany's V2 program. The Atlas's inertial sensing platform used only 2 gyroscopes for pitch and roll sensing, but made use of 3 pendulum-based axis accelerometers to determine its position. The Atlas became the first INS to pioneer the use of sensor fusion via external radio guidance. These early variants of the rockets relied on ground-based guidance updates from one of the first transistor-based computers, designed by Isaac L. Auerbach. The Atlas rocket series operated on the concept of delta guidance, which is based on the adherence to a planned reference trajectory. By the 1960s, the Thor ICBM system and the derived Delta rocket program would result in one of the most versatile rocket systems ever produced. The Thor system employed a new dogma of guidance known as Q guidance. This concept consists of a relatively short boost phase during which the missile's propulsion system operates, followed by a ballistic phase during which the missile coasts to its target under the influence of gravity. The objective of Q guidance is to hit a specific target at a specific time with no reliance on a reference trajectory. This flexibility was a direct result of advancements in computing power and miniaturization. The guidance and control equipment is housed in the forward section of the second stage and provided guidance, sequencing, and stabilization signals for both first and second stages. The system contains 3 gyros, 4 accelerometers, and conditioning electronics, and a guidance computer that processes inertial sensor data to obtain attitude reference and navigational information, while providing continuous guidance correction signals based on a comparison of the instantaneous orbit to the desired mission orbit. The computer also issued pre-programmed sequence commands and provided control system stabilization logic for both powered and coast phases of flight. First and second stage electronic packages receive the guidance commands from the guidance computer in the second stage, and in turn drive the servos for the engine gimbal and control gas jet operations. Computer-based INS technology soon became critical to the aerospace industry, especially as the space race ensued. In aviation, the first fully operational INS for aircraft was developed in the 1950s for the B-52. Known as the N6 Inertial Navigation System, the system represented a significant technological breakthrough, allowing for much more accurate and autonomous long-range navigation than was previously possible. In civil aviation, the Delco carousel was becoming a popular partially automated commercial INS. This system used a gyroscope and accelerometer-based inertial measurement unit as its reference, a digital computer to compute the navigation solution, and a control panel mounted within the aircraft's cockpit. It was used for long over water and over the North Pole aircraft navigation. Flight crew would enter up to 9 individual waypoints by their latitude and longitude, and then the starting location in latitude and longitude. The system was so effective that it would be adopted for use in military aircraft, and remain in use well into the 1980s as various evolved variants. In 1913, French physicist Georges Sagnac had set out to detect the Earth's motion through the hypothetical ether, believed at the time to be the medium through which light waves propagated. In his experiment, Sagnac split a beam of light and sent the 2 beams in opposite directions around a rotating platform. When an object rotates, the light beam moving against the direction of rotation travels at a longer path compared to the beam moving with the rotation. This difference in path length causes a phase shift in the light, resulting in an interference pattern that can be measured. Known as the Sagnac effect, this characteristic would prove to be particularly useful for detecting rotational motion. In 1963, the first experimental ring laser gyroscope was demonstrated in the US by W.M. McKeck and D.T.M. Davis Jr. at the Sperry Corporation. This groundbreaking development led to the widespread adoption of ring laser gyroscopes in various high-precision navigation systems. Ring laser gyroscopes include a ring laser setup where counter-propagating beams circulate. A key feature of this design is the absence of moving parts, except for the Ditter motor assembly and laser lock mechanism that are used to mitigate lock-in, a condition that occurs at low rates of rotation where the counter-travel distances become very similar. This lack of mechanical components eliminates friction, a common source of drift in conventional gyroscopes, thereby enhancing the stability and accuracy of the ring laser gyroscopes. Ring laser gyroscopes can operate in excess of 60,000 hours between failure, with less than 1/100th of a degree per hour of drift. By the 1980s, ring laser gyroscopes, along with their fiber optic-based counterpart, began to appear in the INSs of a broad range of civilian and military aircraft. Their size and reliability also made them well suited for missile use. Additionally, with the advent of GPS in the late 1970s and the increased power of embedded computing, INSs would slowly evolve into hybrid systems that fuse positional data from GPS and other non-inertial sensors, such as magnetometers and terrestrial radio navigation systems, to produce incredible levels of navigational robustness and accuracy. During the 1980s, another theoretical method for measuring rotational rate was being developed into a practical mechanism called a vibrating structure gyroscope, or Coriolis vibratory gyroscope. This type of gyroscope uses the principle of vibration to measure rotational rate. The key principle behind its operation is the Coriolis effect, which affects a vibrating object when its support structure rotates. As this rotation occurs, the vibrating object tends to keep vibrating in its original plane. This results in a Coriolis force exerted on the support, and by measuring this force, the rate of rotation can be determined. In the mid-1980s, GEC Marconi experimented with various metal alloys with attached piezoelectric elements to produce a functional sensor. By the 1990s, various other configurations of the concept would be explored. Piezoceramics, in particular, proved to be incredibly durable, being able to handle up to 300 Gs and 500,000 hours of continuous operation. Other explored variations used tuning fork structures, spheres, wine glass configurations, and various other geometries. Ultimately, the technology would intersect with the emergence of micro-electromechanical systems, or MEMS, and by the beginning of the 21st century, a new spectrum of microscopic vibrating structure gyroscopes would be paired with accelerometers on completely embedded inertial measurement units that were not only small in size and durable, but incredibly inexpensive to mass produce and interface with software. While not as accurate as their macroscopic counterparts, these advantages allow for capabilities once reserved for massive aerospace and defense programs to be had by millions of consumer products such as smartphones, personal navigation devices, game systems, and vehicle safety systems. Like many of the legacy mechanical systems that now interface with computing, the future of inertial sensing lies in the power of the software that it drives. This evolution will undoubtedly expand their applications beyond current realms, potentially enabling more immersive virtual and augmented reality experiences, more responsive autonomous vehicles, and advanced personal navigation systems. Additionally, the fusion of gyroscope data with artificial intelligence and machine learning algorithms promises to open new frontiers in predictive analytics and motion-based user interfaces. As these technologies continue to evolve, gyroscopes will play a crucial role in shaping our interaction with the digital and physical worlds, making motion sensing more intuitive and integrated into our daily lives. A quick reminder to secure your own digital navigation. Get an exclusive NordVPN deal plus 4 extra months at nordvpn.com/newmindvpn. It's completely risk-free with their 30-day money-back guarantee.